All right, now that we have a brief introduction to cryptanalysis, now let me show you an example so that we can understand how differential cryptanalysis works. So in literature, people always give the attack on this, but understanding that attack is not that easy, and sometimes it requires more information. Some people use Hayes tutorial, but again, there it is hard to understand the probability theory or why we are doing it. So since present is a very easy and simple cipher to understand, I will give an differential cryptanalysis attack on present to explain how the differential cryptanalysis works. So let's recall what present looked like. So it was an SPN cipher, substitution permutation network. So it had three layers: key addition, substitution, and permutation. So in the substitution part, here you have the confusion, and here you have the diffusion. So now we have to focus on how these layers affect our differential cryptanalysis, or how can I come up with an idea like differential cryptanalysis so I can bypass these layers. So this is the main idea. Okay, so recall that each line was representing a single bit, so we have 64 lines. At the first layer, you XOR your input with your 64-bit round key, not your master key. Then every 4 bits is replaced with another 4 bits by looking at this table. So this S box is in parallel repeated 16 times. And then you perform the permutation, which simply changes the bits of the places. So this bit stays at the same place. So in the next round, it will be here. This bit goes to the position 16. So in the next round, it will be the first bit of S4, and so on and so forth. So question is, we mentioned that differential cryptanalysis actually makes a small modification in the input and tries to follow that change in the intermediate steps. So question is, how these layers affect those changes. So let's start with the idea. So let's start constructing with the differential characteristic. Okay. Assume that we are encrypting two inputs, I and I prime. Okay. With difference, I XOR I prime is alpha. So here we assume that we have control over these I and I alpha, and so I prime, sorry, so we have control in alpha. But it doesn't matter. Just assume that we have two inputs and we know their XOR. So the question is, how the key addition, substitution, and permutation layer affects this difference, okay? Let's look at the first layer, key addition. So in the key addition, you XOR your input with your round key, right? So for the first input, the output will be I XOR K. In the second input, the output will be I prime XOR. Again, since the round key is the same, it will be the same key. Since both inputs are encrypted with the same key, their difference is still the same, because after the key addition, the first input will become this, and the second input will turn into this. But if you XOR this, you will end up with I XOR I prime, which we already know the difference. Okay, so since key addition is just an XOR operation, and our difference is determined by an XOR operation, this alpha is not affected by the key addition layer. Okay, but in differential cryptanalysis, don't forget that alpha is not the output. So I'm performing one encryption here and another encryption here. So our input is I, our second input is I prime, but their XOR is alpha. Okay, so some people confuse this. They think that alpha is the output. Alpha is not the output. Alpha is just the difference. Okay, so you add key, round key to both of these inputs. So you move one layer forward, but their XOR is still the same. Okay, then question is how the substitution layer affects. So the problem here is that we don't know the exact values of the input, because since we don't know the K, we don't know the value I XOR K. So if we go back to picture, so I know the I value here, but once I XOR it with the secret key, round key K, I don't know the value here. So I don't know what will be the input of S. So if I don't know the input, I cannot know the output, right? So this is our main problem. We don't know the exact values of Si XOR K and Si prime XOR K. Since we don't know these inputs, we don't know the outputs. So we cannot exactly know the difference after this operation, S-box operation, okay? But we can analyze the S-box to see which input differences provide which output differences. So here probability theory comes into play, okay? So now we cannot say something in as a certainty, but we can say with probability this might happen, okay? So we will talk about this. But let's look at the permutation layer. Present permutation layer only changes the places of the bits. So if the input has a non-zero difference at the ith bit, then the output has a non-zero difference at the pith bit. So p is the permutation here. So this means that assume that you are performing two encryptions. So assume that in one of them this bit is 0, and in the other one that bit is 1. So their difference is 1. So after the permutation, this bit stays here, and in the other part, that bit stays there. So their XOR at this bit is the same, because this permutation leaves this bit at the same place. But if the same thing happens to this bit, so again, we are thinking about pairs. In one encryption, assume that the output is 1, and in the other one, that output is 0. So their difference is 1. So this difference actually is moved to here and will be here. So permutation layer actually permute your difference, and that's it. So you, again, with probability 1, you know what is going to happen if you know the difference here. So the only place that creates a problem is the S-box layer, because I'm not affected by the key addition layer. I'm affected by the permutation layer, but I'm affected with directly with the permutation. So if I know the permutation, I know how it affects the difference. So now the only problem is here. So if you remove this S-box layer, actual Cipher does not provide any confusion. So with probability 1, you can say that if I flip this bit, I will know what will happen after 10,000 rounds. Okay, so your main security comes from the S-box. So this is why we want to have good S-boxes. So let's look at the presence S-box and consider every possible XY input pairs with X XOR Y is I. So I will change this I value and count the output differences where SX XOR SY equals to J. So here I'm actually fixing the input difference of the S-box with I. Then I'm counting the output differences J. Okay. So this way I can construct a table with this count as the ijth entry. Okay. So for instance, if you fix I equals to 1, this means that every XY pair where their XOR is 1. So this includes 0 and 1, 2 and 3, 4 and 5, 6 and 7, and so on. If you choose I equals to 2, this means that 0 and 2, 1 and 3, 2 and 4, 2 and 0, sorry, because you XOR 2 with 2, and so on. So the choice of input difference actually determines your input pairs. So you put those pairs to S-box. For instance, assume that our I is 1. So I'm focusing on pairs like 0, 1. I perform the S-box operation. Now the output is C and 5. Their XOR will be our J value. And in this scenario, since we are focusing on every possible XY, so I'm focusing on 0, 1 when I took X equals to 0. Since I fixed the input difference as 1, Y has to be 1. But if I choose X equals to 1, then Y now becomes 0. So having XY and YX actually gives the same output. That is what I'm trying to say. Because 0, 1 and 1, 0 in terms of output XOR will be the same. Okay, so for this reason, in our table, we will see even values, not odd values. Okay, this is why this table is filled with zeros, twos, and fours. Okay, so this table actually says that, for instance, if your input difference is 4 in hexadecimal notation, you look at the fourth row and you see a lot of zeros here. This means that when your input difference is 4, you cannot see the output difference 1. Okay, but you see with 4 many times, you see the output 5. So this means that 4 over 16 times, you will see 5. This means that it has probability 1 over 4, or 2 to the minus 2. So this table tells you when you have the input difference, it tells you what kind of output differences you may observe with what probability. Okay, so this is why we are actually constructing such a table, and this is called difference distribution table, DDT in short. Okay, this is why probably you heard it, it is famous in this way. So this is the table you are going to use, because let's go back to our theory. We said that if I know the input difference, I know the output difference of the key addition layer, I know the output difference of the permutation layer, but I don't know the output of the substitution layer. So now I can say the output will be this with this probability, okay, by looking at this table. That is the main idea. So let's talk a little bit about DDTs. The highest value in the DDT, except the first entry, is called differential uniformity. Because if you look at the first input, this means that you are introducing zero difference. So you are actually talking about XX. So their XOR is zero. So their output will be SX, SX, and their XOR will be 0, 2. This is why this value is always 2 to the n, where n is the size of the S box. So if it were an 8 by 8 S box, you will see 256 here. So we are actually not interested in the first row or first column. Okay, we are focusing on the inside. So at this part, the highest value you can see for this S box is 4. So for present, the differential uniformity is 4. Okay, it could be worse. There are some DDTs where you will see 6 or 8s, maybe 10s. I don't remember, but I think you will see them. So our aim for the designer to have low values here, so to reduce the probability. So I already said that these values has to be even, and I'm also saying that we want them to be low. So in the best scenario, you would only see 2s and 0s. This would make that the differential uniformity is 2. So you might say that, okay, why a present does not use a DDT table which has differential uniformity 2? The thing is that we actually search every possible 4x4 S box. Actually, we can put them into FIV classes and look at the classes to check all of the possible S boxes, and we observe that there are no two uniform DDTs when the S box size is 4x4. So this is one of the best you can get in terms of differential cryptanalysis, and you cannot see a 4x4 S box which is filled with 2s and 0s here. Okay, so high differential uniformity provides characteristics with high probability, hence lower is better. For the attacker, of course, high is better, but for the designer, low is better. Values in DDT is even because the pairs XY and YX provides the same difference. Thus, the theoretically best achievable differential uniformity is 2. For odd n, we can construct such n by n S boxes where the differential uniformity is 2. But for in practice, most of the time we work on bytes and so on, so we prefer even numbered S boxes. So for n equals to 4, there is no such an S box which has differential uniformity 2. So this actually, for a long time, gave the impression that actually for even sized S boxes, maybe there are no two uniform S boxes, because, for instance, AES using 8 by 8 S box, so n equals to 8 there. So AES S box is one of the best S boxes we have in practice, and it has differential uniformity 4. So this gave the idea that since we cannot find good S box in terms of differential uniformity, maybe when n is even, there is no such an S box. But this idea actually destroyed in 2010 because Dylan found the two uniform S box where n was equals to 6. So you can have a 6 by 6 S box which has DDT with two differential uniformity. So now the big open question is, can you find the two uniform 8 by 8 S box? Because if you can find, then you can say that, okay, I found an S box that is better than AES S box. And you can use that from that point on in any of your designs. So this is a huge open problem which couldn't be solved since 2010. And we cannot search the whole space because the whole space is really large. We are trying to come up with greedy or heuristic algorithms to search meaningful parts of the space to see if we can find such a thing. So far, these ideas failed, so we couldn't find one. But this doesn't mean that there isn't any. Maybe there isn't two uniform 8x8 S-boxes. We don't know it. It is an open problem. But if there is, we don't know if we can find it. Dylan found this one due to a very mathematical good construction. And that idea does not apply to A. So this is why Dylan couldn't come up with a generic solution for every even numbered S-box. But for the 6x6, he didn't search the space. He constructed this S-box by focusing on the mathematics. Okay. So President's S-box was chosen in a good way because it is differentially 4 uniform. It does not contain fixed points. This is one of the criteria the designers focused on. They said that when you choose an x, you never obtain the sx equals to x. So it doesn't have a fixed point. You can easily see this from here. For instance, 0 goes to c, 1 goes to 5. So nothing goes to itself. This is a design choice. This doesn't have to be like this, but generally we don't like fixed points. But sometimes in order to have better performance, you might, have to make a trade-off between security and performance. So we have many lightweight designs where 0 goes to 0. Okay. Because in hardware, that S-box requires less area and so on. Okay. But President focused on not having a fixed point, but also they focused on one thing. 1-bit input difference never provides a 1-bit output difference. So when your input difference is 1, 2, 4, or 8 for x and y, then the XOR of the output of the S-box is never 1, 2, 4, or 8. This is important because this way, when the difference has low weight, this means that S-box kind of increases the number of non-zero bits differences. So this way, you kind of prevent some of the good characteristics, let's say. So if you go back to the DDT table, you can see it from here. So if your input difference is 1, as you can see, you don't see 1, 2, 4, or 8 because you have zeros here. Similarly, if you look at 8, you won't see 1, 2, 4, or 8. Okay, here. This is a design choice. Actually, if they didn't have it, we could find longer differential characteristics, which will be meaningful in the following slides. So in literature, there are some long distinguishers for differential characteristics for present. One example is this 4-round iterative characteristic. I will explain what it is, and I will explain why I call it iterative. Okay, so it says that choose 2 inputs so that their input difference is only on these 2 S-boxes where the difference is 4. So if you go back, so they give the difference to x0 and x3 as 4 in hexadecimal. So if you go back to picture, what they're saying that assume that we have an input, then modify it as follows. So for the S0, flip this bit so that the difference becomes 4, and S3 flip this bit. So you only change 2 bits. Then we want to see what will happen to these 2 bits. So after the key addition layer, nothing happens, only these 2 bits are flipped. But after the S-box, we can only say that it will be this with some probability. So in this characteristic, they say that after the S-box operation, x0 will have the output difference 5, and x3 will have the output difference 5. But we already seen that having the input difference 4 and having the output difference 5 has probability 1/4. But now we are expecting to see the same in 2 S-boxes. So 1/4 times 1/4 means 1/16, which is 2 to the minus 4. So with this probability, once we have this input difference, after the S-box layer, the output difference will be this. Okay. So permutation layer actually changes the places of these bits. So now it becomes x0 and x8. But since the permutation layer happens with probability 1, this doesn't introduce any problem to us. Now we have a S-box input 9, and we say that the output of this S-box will be 4 with probability 2 to the minus 2. So this is also 2 to the minus 2. You multiply it and obtain 2 to the minus 4. This means that if you look at the DDD table, 9 goes to 4 with probability 1 over 4. So let's go back to DDT and check if this is the case. You look at the 9th row, and as you can see, you see 4 here for the 4. So probability is 4 over 16. Okay. So this is why this is the case, and so on and so forth. Here on the differences with this probability, here it says the input is 5 and the output is 1. But this means that when you go back to DDT, for the 5, you see 1, not 4 many times, but 2 times. This is why 2 over 16, which is 1 over 8, which is 2 to the minus 3. And since you want to see the same output in 2 S-boxes, you multiply the probabilities, so you end up with 2 to the minus 6. Okay? So this means that if you have a present input and encrypt it 4 rounds, then take the same input, only flip these 2 bits, and also encrypt it 4 rounds with the same secret key, but you don't know the secret key, the output XOR will only have difference only in these 2 bits with the probabilities of these multiplied. So it is actually 2 to the minus 18. Okay. So this means that if you take like 2 to the 18 inputs, most probably only one of them will have this output. But if you more input pairs, then you will expect to see this output more times. So this means that if we assume that these probabilities are independent, then the foreground characteristics hold with probability 2 to the minus 18. Input and output difference are the same in this example. So if you go back, we started with giving only the differences to x0 and x3 with this. And after 4 rounds, we still have the same difference. So I can take this table, this table, and put it here again. So this time I construct 8-round characteristic, but not with probability 2 to the minus 18, but square root of it 2 to the minus 36. And this is why it says input and output differences are the same. So we can put the same characteristic below to obtain 8-round characteristics with probability 2 to the minus 36. This is why we call it iterative. You may put it again, obtain 12-round characteristic, but this time the probability will be 54, I guess, 2 to the minus 54. So you might say that, okay, why don't I edit infinitely many times and obtain a very long distinguisher? The thing is that for a random permutation, if you only change these 2 bits and expect to change a very specific output difference where you specify 64 bits, so this has a probability, since the block size is 64 bits, for a random permutation, this has a probability 2 to the minus 64. So this is why you cannot come up with a characteristic that has lower probability than 2 to the minus 64. Okay. So in Wang's paper, they attack 16-round present, and 14-round characteristic is given like this. So this input difference, 64 bits input difference, only these bits are affected. After 14 rounds, the output difference will be this. They, check the S-box DDT and observe this. And they observe that this has probability this. Okay. If we add 2 rounds to bottom of this characteristic, this 14-round characteristic, the output difference should be in the form this. Recall that we have to start with a distinguisher, add rounds, and capture the side key. So this is our distinguisher for 14 rounds. We add 2 rounds to the bottom, and note that this 14-round distinguisher ends with 9 values here. So now we add 2 rounds. By adding 2 rounds, we are just actually looking at what can happen after these 2 rounds. Okay. So if there is an non-zero difference here, this will mean that output will have some kind of difference. Normally, you will say, you would write 4 question marks here. But due to the property in the present, we observe that this this bit cannot have one difference, but it doesn't matter. You have to know that value. So this difference on the S-box affects output, right? This output after the permutation layer is transferred to here, 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 and so on. So actually, this 0 comes here and this 0 comes here. So they will also have some kind of output. I'm showing you this because if you add 2 runs, you will not see any difference on this S-box, and actually you don't need to know that value. So I told you that after you have the distinguisher, you have to, decrypt 2 runs back and check if you see this difference. Because if you see it, then this will mean that you satisfy the distinguisher. But in order to perform the 2-run decryption, you need to know the round keys of these 2 runs. But the good thing is that you don't need to obtain the whole round key, because it is enough to know the values of the effective, which we call active S-boxes. You need to know this 4-bit key XOR here, 4-bit key here, 4-bit key here, and so on, also here, 0 and 2. So that way, for all of those possible keys, you perform the decryption. Also do the decryption for these 2 S-boxes and check if you see the 9. If you see it, you increment the counter for that key. This is how the attack works. So to summarize, to Wang's differential attack on 16 round present, attack procedure works as follows. Data collection is on 16 rounds, so you gather M plaintext ciphertext pairs with the input difference this and the output difference this after 16 rounds. Key guess, partially decrypt these pairs with every possible key bits of rounds 16 and 15 that correspond to S-boxes with non-zero differences, but actually the correct sentence will be active S-boxes. Correct key should have the highest counter. Exhaustive search. Remaining key bits are obtained by exhaustive search, because if you go back, I told you that the effective S-boxes are here. Okay, so 0, 2, 4, 6, 8, 10, 12, and 14. So this means 8 S-boxes are affected, and 8 S-boxes have 4 key bits, which means the 32 bits. Also, you have to guess 4 bits here and 4 bits here. So you have to guess 40 bits, right? So if you are attacking present 80 bits present, this attack in theory captures 40 bits. So you can obtain the remaining 40 bits by performing an exhaustive search with 2 to the 40 encryptions, okay? But in practice, it doesn't work like this. You cannot capture all of the 40 bits, but this is a very technical detail. I will actually briefly maybe mention here. But to summarize, adding 2 rounds to the bottom of the 14-round differential, which holds with probability 2 to the minus 64. And actually, this is only a single characteristic. They combine 24 characteristics with the same probability and output difference. This way, this probability is increased because they are using 24 characteristics. They claim that this attack captures 32 bits of the key with this many 2-round encryptions. Remaining 48 bits require 2 to the 48 16-round encryptions, or this many memory accesses. So activates at most 6 S-boxes in round 16 with input difference 1. Okay, this part. But again, so this is actually one of the problems in cryptanalysis. This attack is obtained in theory, right? They found the path, and they say that they can do this attack with this many encryptions and so on. But actually, if they write the code and perform the attack, they will see that they will not be able to capture some of the bits. Okay, this is due to differential factors that I introduced to the literature a few years ago. So let me briefly mention this theory versus practice. Most of the time, attacks cannot be verified in practice due to the high data, time, and memory complexities. So sometimes you find a 16-run attack which requires 2 to the 60 encryptions. But if you remove a few runs, you can perform that attack in practice. So this is why I always encourage people to perform these theoretical attacks in practice by reducing number of runs, okay? Reduced versions of theoretical attack should be experimentally verified to check if anything is overlooked. Lang's attack should be modified due to the existence of differential factors. I'm not going to go much into detail but I defend the differential factor as follows. Assume that you fix the output difference. Sometimes in some S-boxes, due to this output difference, there is a value called lambda, where you add it to the input, the output does not change. This means that if you are trying to capture a secret key affecting this 4-bit S-box, that secret key, the correct secret key will satisfy this property, but that correct secret key XORed with lambda will also satisfy this property. So you will not be able to distinguish those two cases. Okay, so actually you cannot capture that 4 bits anyway. Okay, so this is this is very theoretical. You cannot directly understand it from this slide, but the main take here is that obtaining results in theory in cryptanalysis sometimes doesn't work in practice. Okay, so I always encourage people to perform experiments, since the the whole attack will require a lot of time and data complexity. Just remove first few rounds so that the attack becomes practical, and perform the experiment there and see if your theory matches the practice. Okay, this is one of the problems we observe in practice.